All right, let's talk about something that I know can sound a little scary, calculus. But I promise you, at its heart, it's way more intuitive and honestly more fascinating than its reputation suggests. So let's just dive right in.
For just a second, forget about math as a bunch of static, unchanging numbers. Instead, look around you. I mean, everything is in motion, right? A car speeds up, a company's profits go up or down, a planet swings around the sun. What if there was a language, a mathematical language, built just to describe and even predict all this constant change? Well, guess what? We have one, and that's exactly what calculus is.
And here is the absolute best part. This whole kind of huge sounding field, it really just boils down to answering two major questions. That's it. If you get these two ideas, you've totally grasped the essence of what calculus is all about. And here they are. First, how fast is something changing right now, at this very instant? And second, how much stuff has piled up over a certain amount of time? One is about the immediate moment, the instant. The other is about the big picture, the total. Let's dig into that first question. So, let's tackle that right now problem. This brings us to the first huge idea in calculus, derivatives. This is the tool for figuring out instantaneous change. So, what is a derivative? It's basically a tool, a way to measure exactly how fast something is changing at one specific moment. We're not talking about your average speed over a whole hour, we're talking about the speed at the exact microsecond you look. Just think about driving your car and glancing at the speedometer. It isn't telling you your average speed for the whole trip, is it? Nope. It tells you your speed right now. 60 miles per hour, at this very instant. That's a derivative, right there in your car. And if we wanted to visualize this, imagine your trip was drawn on a graph. The derivative is like finding the steepness, the slope of that graph at one single spot. Not the average slope of the entire hill, just how steep it is right where you're standing.
And you'll see this idea pop up everywhere, right? We can now ask questions like, how fast exactly are a company's profits growing today? Or how steep is this one little patch of the trail I'm hiking? It's all about nailing down that rate of change at a super precise moment.
Okay, so let's get just a little bit mathematical for a second. But don't worry. If we have a curve described by the function x squared, calculus gives us this new function, 2x. And that new function is basically a simple recipe that tells us the slope, the steepness, at any point we want on that original curve. We've basically created a cheat sheet for the right now.
All right, so that's the whole right now thing. But what about that second big question? The one about accumulation, the big picture over time problem. Well, for that, we step into the world of integrals.
An integral does the complete opposite of a derivative. Instead of zooming in on one tiny moment, it zooms out to see the whole story. The way it works is actually pretty cool. It's like adding up a ton, like an infinite number of teeny tiny little slices of something to figure out the grand total.
So think about questions like this. If water is pouring into a tank but the flow keeps changing, how much water is in there after an hour? Or, if you're driving and your speed is all over the place, what was the total distance you covered? Integrals answer these kinds of questions. They find the total accumulation.
And visually, it's a perfect contrast. If a derivative is the slope at one tiny point on a graph, the integral is the entire area underneath a whole section of that graph. It literally represents the sum of all the little parts.
Okay, remember that math example we had? We started with a function, x squared, and we split it apart to find its rate of change, which was 2x. Well, integration lets us do the exact opposite. If we start with that rate of change, 2x, and integrate it, we get our original function, x squared, right back. We're just putting the pieces back together.
Okay, so we've got these two huge concepts. One is all about splitting things apart to find that instantaneous rate. The other is all about putting things back together to find the total. So how do they relate? I mean, this is where the real magic of calculus happens. Let's just put them side by side for a second. Derivatives, they measure the rate of change. Integrals, they measure the total accumulated. Derivatives are about splitting things apart. Integrals are about putting things back together. Are you starting to see the pattern here? They're mirror images of each other. That's it. That is the big secret. They are opposite processes. One undoes the other. It's kind of like how multiplication and division are opposites, or addition and subtraction. It's that same perfect inverse relationship.
And this incredible, powerful, mind-blowing link. Yeah, it has a name, and it's a big one. It's called the fundamental theorem of calculus. It's the powerful idea that connects these two halves and turns them into one beautiful, unified system for understanding our world.
Okay, cool name, but why should you care? Why is this old theorem so important today? What's the big deal?
Well, because it gives us the language. For the first time in human history, we had a way to accurately describe a universe that is never, ever standing still. It's the mathematics of motion, of growth, of change itself.
So what does that really mean for us? It means that for almost any system that changes, from a planet's orbit to the stock market, we can use these two connected ideas to do two incredibly powerful things: pinpoint a rate of change at any instant and calculate a total accumulation over any period.
So you see, calculus isn't just some dusty old math class. It's like a new pair of glasses for looking at the world. It gives us this amazing language for change. So my question to you is, what change will you start to see now?